Well, dear, welcome back. So, you have started watching videos on execution level control, and in that context, we are actually studying the dynamics of a second order system with the help of mass spring model. Although you may argue that this understanding oscillation and of the dynamics of a second order system is not directly related with execution level control, but yes, for understanding execution level control and many other fields, I believe that this oscillation of or the dynamics of second order system is very, very important. So let us start our journey. So the last day, last lecture, we discussed about the behavior of the mass spring system when it is only excited by perturbation. That means small excitation. Okay. Uh, so this is a mass spring system, and then you have just perturb. That means um, our dynamic equation was like um, this, no? Mx double dot plus kx equal to 0. That means there was no permanent excitation to the system. But today we will move further that what if the same model is excited by a force, external force now, P. Okay. P could be sinusoidal like this, or it could be constant, could be anything. But in a general way, let us assume that P equal to P0 sine omega ft. Omega f is the frequency, circular frequency again, of oscillation of the force, external force, okay, external force, okay. So that's why f, omega f, to distinguish itself from that is omega, which is natural frequency of the system. Again, we are considering only single degrees of freedom. That means we have only x, okay, and this is our direction of motion, okay. So this is our direction of motion, and if we draw a free body diagram using D'Alembert principle, as earlier, say, which says that if a dynamic system is actually um, acted on by a force which we call inertial force in the direction opposite to the direction of motion, which is mass time acceleration, then the dynamic system becomes a pseudo static system, which helps. So all the equilibrium condition you can apply here. So we are applying. So you see, as usual, we have this inertial force, spring force, and external force. Okay, G we are not considering. You can consider, but it will not hardly matter. I told you, right? So because G will be plus here, and then there will be mg. So mg and this mg will cancel out. So G has no role to play here. Okay, so that's why we are not considering it. So mx double. So equation of motion will be mx double dot plus kx equal to p0 sine omega ft. Now, since this type of differential equation has two solutions, as you know, right? Say total solution is x, so x will be xa plus xb. Okay, so xa is known as complementary solution, which is equivalent to our putting it 0. Okay, and another is called particular solution, which is actually equal to some constant sine omega ft. Again, trial solution we have made, right? So we are trialing, making a trial that okay, it is a second order system, two constants will be there, and in particular solution, another constant we have applied c sine omega ft. So if, as usual, if this is the solution, particular solution, and complementary solution we have already deduced earlier, then what will happen? We'll have to, this will satisfy this equation, right? So try to just differentiate x double dot, okay, equal to minus c omega f square sine omega ft. Okay, and then you see I am putting these values here instead of x, xb, right? So minus m omega f squared c sine omega f t, okay, plus k x, in place of x we have c sine omega f t, okay, equals to p, okay, equals to p0 sine omega f t, okay. So you see, just little algebra, sine omega f t, sine omega f t, sine omega f t cancels out, okay. So this becomes, so C immediately, the constant can be figured out with the help of system parameter as well as the external forcing parameters, right? P0 divided by K minus m omega f square, correct? Okay. So we have this from 3. Now we have xb equals to c sine omega f t, okay, c from 3. Thus xb equals to this. Here it will be actually for completeness, let us put, okay. So this will be here, sorry about that, okay. Here it is beautifully shown. So now simplification we are doing p0 divided by k, means we are dividing both numerator and denominator by k. So it becomes 1 minus omega f square divided by omega square. Omega f is the circular frequency of the external force or external excitation. Omega is the circular frequency of the system, okay, natural frequency. So you see, now putting omega square equal to k by m, as you know. So 1 by omega square will be equal to m by k. So instead of m by k, we are getting omega f square divided by omega square, right? So we are now having a ratio of two circular frequencies, forcing circular frequency and natural frequency. Let us denote it by r, okay? It's a ratio. And let us call x not equal to p naught divided by k. So then in a simplified way, xb becomes equals to x0 divided by 1 minus r square sine omega f t, where is equals to xb equals to x. In place of this, we are putting x, sine omega f t. So now let us see, this is a solution, right? This is a particular solution. So let us see what happens. Suppose now here this is our excitation, sinusoidal excitation, p equal to p0 sine omega f t. If this is the case, then what is happening? X versus omega f t, if we just plot, then we are seeing that if r less than 1, so this is less than 1, so this quantity is positive definite, so x is positive definite. So in that case, so xb equals to actually some constant, the amplitude of oscillation times sine omega f t, okay. So this is, and this forcing the forcing function and this resultant, the displacement function, they are in phase because this is positive definite. Now what will happen case 2, in case of case 2, if r greater than 1, that means omega f, circular frequency, forcing circular frequency, is possible, right, is larger than system natural frequency. Natural frequency is constant. Once k and m are determined, they are constant, right? So forcing frequency is external one. So what if this is greater than 1? Then you see the this quantity will be negative, okay, negative definite, right? So you see, if this is negative, then this is my forcing function, and this is my excited displacement versus so excitation response. This is a response, okay. This is the action and this is the response. And you see, since now x be equal to minus x sine omega f t, then this will be in opposite phase, okay. So, or you can call it x b equals to x cosine omega ft. So this is a cosine function. So this is a sine function. So this external excitation and system's response, they are in opposite phase. Just observe from a very simple relation, it is actually important observation. Now what if r equals to 1? Then what happens? Eh? That means system's natural frequency and external force which is acting on the system, its external forcing functions frequency, if they matches, if they are equal, then what will happen? This is equals to 1, and then x0 divided by 0. So something divided by 0, amplitude of oscillation, this is infinitely large, but we cannot stop by telling that it is infinitely large. We'll have to figure out what it is. So when we were in school, we will leave it here that okay, resonance will occur because the amplitude of oscillation is infinitely large. Okay, but we will try to understand here how to have a solution for the resonant condition. Okay, mathematically cleaner solution we'll have to put. Now look here how to do that. R equals to 1 means omega f equals to omega. Okay, so we are rewriting this. Okay, now let omega f is almost equal but slightly less than omega. So this is my assumption. So that it will be positive definite. Okay, so omega minus omega f equals to 2 epsilon. 2, why I am writing 2? Mathematical convenience. Okay, you can write 1 also. Okay, so but I am writing, afterwards you will see something, the expression will be the way we want. That's why 2 I have added. So what is epsilon? Epsilon is a very small positive quantity, smaller than you can imagine. Also note that omega plus omega f, this is almost equal to twice omega f. Isn't it? Because if they are similar, same, I can put omega f in place of omega. So this will be equal to twice omega f. Now, omega minus omega f times omega plus omega f will be from 9 and 10 to 4 epsilon times omega f. Let us call it 11. So omega square minus omega square equals to 4 epsilon omega f, you are getting. Just now rewrite the solution like earlier. Okay, x total solution will be equals to xa complementary solution plus particular solution, and x will be equal to, this is our complementary solution, a sin omega t plus b cosine omega t plus particular solution which we have deduced earlier, particular solution. Particular solution actually, this is omega minus omega square times omega. So from here it is coming omega square minus omega f square. So we are rewriting this in this form. You understand? All of you? This we are rewriting instead of this because this is not able to give me a clean solution. So I am going back. From here, we are actually rewriting it in this form. You can just take a notebook and do this. And we are getting this. Okay. So this is your xb. Now putting the initial values, that is boundary condition, that okay, let us assume that at t equal to 0, x equal to x0, and at t equal to 0, x dot equals to x not dot. Okay, so a equals to we have reduced it. You can see, you can put it will be x not dot divided by omega minus this term at equal to 0 if I assume this. So a will be figured out with this and b will be two constant you can figure out by putting this solution here. Okay, that's we did it earlier. Now we can write x equals to minus this quantity sine omega t plus, okay, so this now a and b I am putting these values, and plus this quantity. So this is coming out, and then you are getting sine omega t minus sine omega f t minus sine omega t. Okay, because very without loss of generality, I can assume that, okay, what I can assume that at t equal to 0, x equals to x naught equal to 0. At t equals to 0, x dot equal to 0. Then you will get this. With a notebook you can do this. So my solution becomes, without loss of generality, is simpler, right? So now sine A minus sine B. So using trigonometrical identity, you can write down in the product form twice sine this plus this, okay, which is this, into cosine of this plus this divided by 2, sine of this minus this divided by 2. Okay, so this is my solution. Okay, so in this part B, let us try to utilize this and start and continue our discussion here. Okay, so x equals to, now see omega, here we are putting 4 epsilon omega f, 4 epsilon omega f, 2 is already here, so 2 cancels out, and this actually takes this f, okay, equal to minus p0 by m divided by this sine of epsilon t times cosine omega f t. Okay. Now when omega f is very near to omega, is almost equal, then epsilon will be 0 and sine near about 0, this is meaning that very small quantity, and sine epsilon t can be replaced by epsilon t, and we are doing that and rewriting it in this form. This is p0 by k equal to h0. This epsilon cancels out, then x naught omega square divided by 2 omega f t cosine omega f t equals to minus x naught omega f by 2 times t cosine omega f t by putting r tending towards 1. Now you see, this is the actually solution, though this is 17. So 17 is the solution for resonant condition, and see how the interesting shape of the response. So when you are exciting that mass spring system with a forcing frequency which is almost equivalent to the system's natural frequency, then not that the amplitude of oscillation becomes momentarily infinitely large, but instead this is the envelope. Within this envelope you can just make a MATLAB plot or any plot, okay, Python plot, okay, and you will see that within this envelope, since this minus sign is there, so it will start in this direction, minus direction, okay, and it will oscillate like this, okay, and in an unbounded way, the oscillation, amplitude of oscillation will go on increasing, and this is actually called, this phenomenon is called resonance, okay, and this is dangerous, when this is exactly almost equal to system's natural frequency. There are so many story and real story, of course. People did not know, when people did not know about resonance clearly. So one bridge was constructed with bridge is actually, every structure has a natural frequency of oscillation. Okay, so uh, it has stiffness, so that's the beauty. No, it need not be only physical spring or mass. Spring is actually stiffness. It may be concrete. It has some stiffness and mass. Okay, it has some mass, so it has a natural frequency. And if you excite the bridge with some forcing function, which is whose frequency is equivalent or almost equal to the natural frequency, then its amplitude of oscillation will increase and the bridge will collapse. And that exactly happened when soldiers were actually marching in a rhythmic way on the structure, bridge structure. Then all on a sudden, the after some time, the oscillation was used, and then uh, bridge failed. And interestingly, in laboratory, we actually demonstrated this with a laboratory setup. Very interesting. Perhaps many of you have done this. It is visible very much. Okay, that when omega and omega f will match, then amplitude of oscillation will increase asymptotically. And that's why that's called resonant condition. And in many mechanical structure and other structure, this resonance is bad because structure will fail. Structure is failing not because of the strength of the structure, but they are failing because of the resonant phenomena. So in those situations, what will happen? What, for example, in this bridge condition, if you want to set the bridge, so ask the soldiers, okay, do not follow any steps, just randomly you walk past the bridge, and if they do that, then bridge will be safe because structurally it is sound, strength-wise it is sound. Okay. On the other hand, in many situations, the resonance condition is desirable, especially in communication, electronic communication. And you see, we have a receiver transmitter and receiver signal, receiver end. We want resonance condition to occur because even if the received signal is very weak, due to resonant condition, we will get sufficiently large amplitude of oscillation. So depending on the application, this could be desirable, this may not be desirable, like that. Okay. Now related to this, once we have already done so much of effort, of course simple effort, and we have deduced the solution, total solution, just doing some looking here more closely actually, more closely, we can understand another condition which is not exactly resonant condition, which is called beating, Beating. Okay, see, just we are rearranging it, means this term is coming over here, this term is coming over here. Okay, and just x, sorry, here, not here. If you closely look, this solution. So what we are getting, we are putting it here and this term here, and this is becoming, and putting them separately. Okay. So the when this omega f is not exactly equals to omega, but very close, very close. Okay, very close to omega, then the oscillation, amplitude of oscillation will be given by this same 16 equation we have rewritten actually. And what it is telling, that okay, there is a sign epsilon t, which is, epsilon is very very small quantity, smaller than what you can imagine. Okay, so this is the concept of epsilon. And here is another cosine omega ft, and compared to epsilon, this omega f is large. Okay, so omega f is very very large compared to the epsilon. So then what is going to happen, as if I can just imagine a sinusoidal wave like this. Okay, sinusoidal wave like this. Okay, and minus over here. So this is an envelope. This period of oscillation is 2 pi by epsilon, which is period of oscillation is time period is large because epsilon is small. So within this envelope, you see many times cosine oscillation is taking place, and it is starting from negative. So we have from negative in this direction, and then it is going on oscillating within this envelope. And beautiful, again MATLAB plot, if you do with this expression, you will get this condition, that is the amplitude of oscillation is building up, again coming down, again building up, again coming down, again it will build up, again it will come down. So this phenomena is called beating. Okay, so beating is definitely not desirable, and perhaps you have seen, say, I have observed when I was child without knowing that the beating it is called beating. Say in India wedding party house, we have generator because the power situation is not reliable, so generator is there. And when really power fails, then you start generator. So generator is vibrating. It has some natural frequency of oscillation, and it is actually standing on a structure. So structure has some natural frequency, and this generator is actually external frequency it is inducing. And if the matches, and the vibration isolation is not there, means you have not put damper, sufficient damping is there, then what will happen? That due to this vibration of the generator, which is a moving structure, okay, so that vibration will be induced if you are not isolating that generator from the floor. And what will happen? Beating condition will happen if the structure's natural frequency and generator's frequency matches, and a kind of humming sound you can observe, like that. And you can, in a funny way, you can just put it in that way. It will build up, it will die down, build up, die down, build up, die down. So in a movie Three Idiots, when somebody asked the student that how a motor starts, he actually made similar kind of sound. Anyway, so this is a little bit fun. So, but this phenomena is called beating. So resonant phenomena is this resonant condition. Sometimes it's bad, sometimes it is good. But if beating is happening, then it is actually not desirable. How you can avoid beating? Okay, there are several ways. You will have to isolate. You can put some damper between the excited force and the system where this excitation is induced, and many other things, right? So beating can be observed, and you can exactly predict that what will be the nature of the beating, and you can just eliminate it by suitable active control. So that's all I wanted to share with you. This is two very important phenomena for mass spring model when it is excited by a forcing function, external forcing function. Okay, and these two phenomena will can be observed. One is resonant condition, another is beating condition, because you never know what is omega f. If omega f is very near to omega, resonance. If not very near but within vicinity of omega, this beating will happen, and nature of the oscillation will be like this. So that's all, and we can now next time we'll extend our discussion on mass spring damper. We are understanding second order system using mass spring damper model, which is more practical model. And you see the solution of such a dynamic second order dynamic system. What is the behavior of the solution? Very important behavior we will observe in the next class. Till then, stay safe and have a nice day. Bye bye.